Assalamualaikum warahmatullahi wabarakatuh and hi to all my students. This video lecture is continue from latest video which is chapter 3. So this video is about predicate and quantifier. Okay, so first let's look at predicate. Okay, predicate is essentially a sentence that give information about the subject. Usually we write predicate as a P X, okay, where X is referred to the subject of the sentence. Okay, let's say we have a sentence from this example, from the slide, we have Yusuf is a computer science student at UMP. So this is a sentence where Yusuf, okay, let's change the color. Yusuf is a subject of the sentence. Okay, if Yusuf is a subject of the sentence and the rest of the sentence is a predicate. Okay, so this X, Px, this X refer to Yusuf. For this sentence, this X refer to Yusuf. Okay, the same goes if the sentence is logic X. X is a computer science student at UMP. So the same, X is a subject and the rest is a predicate. Okay, and then usually, and then the true set for the predicate is, okay, usually we will set a domain. So each subject has a domain, okay, called D or anything we can use as a domain, we set as a domain. So the true set of the predicate is the set of all elements X in domain D that make the predicate true when all the value of X substitute in Px. Okay, so usually the true set we will write as bracket for X in domain, for X has elements in domain such that Px. Okay, so we read this as a for all X in domain, X is element in domain such that Px. Okay. Okay, let's look at example for a better understanding. Alright, for example, here. The predicate is Qn is a, where n is a factor of 8. Alright. And then find the true set of Qn if, okay, here the domain is given, domain of n is Z positive. Okay, Z positive is a positive integer. Alright. Okay, so the factor of 8 is what? Factor of 8 is 1 times 8, 2 times 4. So the factor is, factor of 8 is 1, 2, 4, 8. Hence, the true set for the Qn, the true set is 1, 2, 4, 8. Okay, because the domain that we set here is positive integer. Okay, for example B. B is domain for n is the set of all integer. That means the factor of 8 can be negative also. Here, let's say we have negative 1 times negative 8 equal to 8. Negative 2 times negative 4 also equal to 8. So the factor of 8, we have negative 1 added negative 2, negative 4, and negative 8. So here the truth set for this QN is 1, 2, 4, 8, negative 1, negative 2, negative 4, negative 8. Right? So that is all about predicate. Okay, next we look at quantifier. Okay, quantifier is referred to the quantities. Alright. Okay, the drawing. Alright, quantifier refer to quantities, and quantifier has quantifiers has two types, which is universal and existential. Alright, so what is the difference between universal and existential? Existential. Alright. Okay, let's here. The predicate for universal, the predicate is true for every element. While existential, there is at least one element under consideration for which the predicate is true. Right, so first look at universal quantifier. Okay, universal quantifier, the symbol that we use is V with this dash. Right, this is symbol for universal quantifier, and we read this symbol as for all, or else can be written, can be write as for any, for every, and for each. That means all element in domain must be satisfied to make the predicate is true. Okay. So the statement is written as for all x in element in domain D such that Q x. Okay, or we can write as for x Q x. This is when we don't have a domain. So this when we have a domain such that we set it as a integer or positive integer or real number, so we have write it as here. If we don't have a domain, so we read like this. So this statement is true when if and only if every x in D is true. Okay, and it is false if and only if at least one x in D is false. Alright? Okay, so what about, okay, let's look example first. Okay, for example, we have a domain. Okay, later we okay, example, we have a domain equal to 1, 2, 3, 4, 5. Okay, so what is the statement? Okay, the statement is this. Right, the statement is this. So show that this statement is true. Okay, to show that the statement is true for all, for universal quantifier, we have to show for the all condition of x. So by taking x equal to 1, so 1 square equal to 1 is more and equal to 1. So when x equal to 2, 2 square equal to 1, more and equal to 2 square equal to 4, more and equal to 2. X equal to 3, 3 square equal to 9, 9 is more and equal more than 3. X equal to 4, 4 square equal to 16, 16 is more than 4. X equal to 5, 5 square equal to 25. 25 is more than 5. So all x is satisfying these conditions. Hence, we can conclude that for all x in D, x squared is more and equal to x is true. Okay, so we should. Alright, so that is the universal quantifier. If the question asks for counterexample proving the statement using counterexample. Okay, counterexample. Okay, here counterexample. Counterexample is opposite of the statement. So a value of x for each, value of x for each qx is false. So how to show the statement is false? Okay, let's look at example 2. Okay, example 2 state that consider a statement. Okay, we have a statement for all x in R. R is a real number. X squared more and equal to x. So determine the counterexample to show that the statement is false. Okay. So when we use counterexample, just is enough to show one example is not satisfied. Okay. So for example here, we take x equal to 1 over 2, where 1 over 2 is in a real number in the domain that we set. Okay, so we have 1 over 2 square equal to 1 over 4. So whereby 1 over 4 is less than 1 over 2, so 1 over 5 is not more and equal to 1 over 2. Okay, alright, so hence for all x, we can conclude that for all x in real number, x square more and equal to x is false. Okay, so enough to show one condition is not satisfied to conclude that this statement is false. But to show this statement is true, we have to show for all x in domain is true. Okay, so then we can make a conclusion that this statement is true. Alright, we finish for universal quantifiers. So let's look at existential quantifier. Alright, the second is existential quantifier. Okay, existential quantifier denote symbol as a E terbalik. Okay, this symbol, alright, this symbol, and we read this symbol as a there exists. Okay, or can be read also as a there is at least one, or for some. Okay, but there exists is the most common use lah. Alright. Okay, so the statement is written as there exists X in a domain D such that Q X. Okay, or can be write as for X there exists X Q X. Okay, so this statement is true if and only if at least one X in D is true. And the statement is false if and only if all X in D is false. Alright. So the counterexample for this extension quantifier is to show that the statement is false. Alright, so let's look at example. Okay, example 1 is proving a quantifier. Let's look. Example 1, the statement is there exists M in Z. Z is a integer. M square equal to M. So show that this statement is true. So how to show it? Okay, for this extension, just enough to show that at least one domain, one X in domain is true. So by taking any integer, positive integer, let's say M equal to 1. So 1 square equal to 1. So 1 square, M square equal to M is true. Is true, right? Hence, there exists M in Z such that M square equal to M is true. That's all. Okay. Sebab, because this statement is true in if and only if at least one X in domain is true. So, it's enough for us to show just one example is true, one domain is true, and make a conclusion that there exists M in the domain such that this statement is true. Alright. So let's look if we want to show the statement is false. Alright. To show the statement is false is by using counter example. Okay. Counter example to show that QX is false. Okay, so let's say we have a domain E equal to 5, 6, 7, 8, 9, 10. Okay, we can't use domain like this because we have proof that there exists integer that make this statement is true. So to prove it, this statement is false, we have to set another domain. Okay, then we note that here is the integer in domain that we use to prove. Okay, so we have to show that there exists M in E such that M square equal to M. Okay, to show this statement is false. This statement is false. We have to show all X in domain is false. Okay, so first we take M equal to 5, so M square equal to 25 is not equal to M. M equal to 6, M square equal to 5 square here, 6 square here equal to 36 is not equal to 6, it's not equal to M. M equal to 7, 7 square equal to 49 is not equal to 7. M equal to 8, 8 square equal to 64, right? 64 is not equal to 8. m equal to 9, 9 squared equals to 81, 81 is not equal to 9. Now m equal to 10, 10 squared equal to 100, 100 is not equal to 10. So we have all condition of x in the domain is false. So hence we can conclude that there exists m in E such that m squared equal to m is false. Okay, so that is about existential quantifier, and we also have a combining quantifier where we combine universal and existential in a one statement. For example, we have a statement for every x in Z, there is y in Z. Okay, so that x plus y equal to 0. So this is a sentence. So in a symbol we can write it as. Alright. For all x, for every x in Z, okay, there exists y in Z. There exists y in Z, such that we can use comma or this one, such that x plus y equal to 0. Okay, sorry. Okay, so here if to convert a statement, no, a sentence into symbols. Okay, so we have for every n there is or there exists the same. Alright, this is a true statement. Why? Okay, why? Okay, why? Because, okay, look here. The statement make a claim about ordinary integer x. It says that no matter what x is, something is true and we can found integer y so that x plus y equal to 0. Okay, for example, 1. By taking x equal to 1. So to make it x 1 plus y equal to 0. So y equal to negative 1. So for all value of x, for all element of x in Z, we can find value of y in Z. For example, we have x equal to 5. Okay, so 5 plus 1 equal to 0. So y value is negative 5. So negative 5 is still in Z. Okay, so this is why this statement is true. Okay, so there is another example. You can prove it by your own and also exercise. So with that, that is all about predicate and quantifier. So I will see you on the next video lecture.